Hello and welcome to example problems for chapter 25. Today we're going to solve a whole bunch of problems. The problems in this packet are pretty spread out, mostly because there's a lot of different things I could do with this chapter. The second problem in the packet is the one most similar to what was on the exam last semester, and honestly will probably be the one most similar to what's going to be on the exam this semester also. But there are some other things I want to make sure you know how to do, so I want to go through a few different ideas. The first one is just about AC in general, and it says the output voltage of an AC generator is given by that equation. Now, really, I should say what that equation is. You see, how we define the output in an AC thing is that the voltage as a function of time. That's a lowercase v. Lowercase and uppercase v's kind of look the same when you handwrite them, but just trust me. Will equal the other voltage, which I'm going to write max here. Normally I don't bother, but once again, I want to make sure they look different. The sine of omega t, which can also be written as V max the sine of 2 pi ft, because where omega is just 2 pi f. And I say this is generating over a 20 ohm resistor. So by inspection, what's the max voltage? Well, I can just look at this thing, and this equation says 170 volt sine of 60 pi t. Well, Vmax is that number. So Vmax is just 160 volts. For B, what's the frequency? Well, we know it's 60 pi t, but 60 pi, that means 60 pi must be omega. Well, omega equals 2 pi f. And therefore the frequency is omega over 2 pi, or 60 pi rad per second over 2 pi. So the frequency is 30 hertz. C, what's the VRMS? And this is actually the first bit that you could really expect to see in an exam, me doing that, because VRMS is a rather crucial thing to know. But VRMS is by definition the max divided by the square root of 2. Well, 1 divided by the square root of 2 is 0.707. So that's the same as 0.707 times V max. Square root of 2 is like 1.4 or something, and 1 divided by that, that's what it comes out to be. And so what I'll say, so I just realized something. Let me check something real fast. Okay, good. I'm good. Is that it's just 0.707 times 160 volts, which is 120 volts. And if you say you have a 120 volt outlet, that's actually what it's doing. That's the RMS voltage. 160 volts would be the voltage in the wall. Okay, let's keep going. Keep switching colors, though the color difference isn't big enough to tell, so I switched to a different one. D says, what's the RMS current? Well, the general idea is things like Ohm's law works still. That, that whole V equals I all, well, I can say V RMS equals I RMS all. And therefore I RMS is V RMS over the resistance, or 120 volts over 20 ohms to get a 60 amp circuit. Sorry, 6 amp. 120 divided by 20 is 6, not 60. I misspoke. This keeps going. This is one of the longest. This problem has more parts than any other problem I've ever done, but they're all pretty straightforward. So, E, maximum current. Well, I can get that two ways. I could say V max equals I max all, or I could just say that I RMS equals 0.707 I max, or I RMS equals I max over the square root of 2. Well, both these are exactly the same. I chose to do this way, not by Ohm's law again, saying I max equals the square root of 2 times IRMS. So that's going to be square root of 2 times 6 amps, which is 8.49 amps. It never stops. Average power. This is one of the reasons RMS comes in. We know from a few chapters ago, we can have a few equations for power. We can say power equals VI, or power equals I squared R, or power equals V squared over R. However, when you are looking at the power is going to be switching as the current and potential changes. The average power is assuming you use the RMS values. And so if I'm going to do this, I have to make sure I use the RMS values for any of those equations. Now, I chose to do the VI because I guess I didn't want to bother squaring things. So I'll just say VRMS, that was 120 volts. IRMS, that was 6 amps. And so you get 720 watts. G, what is the current when t equals 0.005 seconds? I'm not even going to bother. Well, I can do this two ways. I can either find the voltage when the current is that and solve, since we have this equation for, well, let's go uphill. We have this equation for the voltage, so I can just plug in that time. Or I could go straight to a current equation. The current equation would just be I equals I max sine of 2 pi ft. Or in this case, I max was 8.49 amps sine of 60 pi t. And I'll just plug in, which will give me a value of 6.87 amps. And the last bit said, hey, for that, did you have to work in degree or radians? Well, the answer is radians. I had to work in radians because that's in radians per second. So yeah, of course it's radians. I said this was a pretty straightforward problem, simpler than anything I would normally give, but kind of gets the idea across of all these things you got to keep track of here. Any questions on that?
Nope, not currently.
Okay. Let's do a real problem then. So let's go a little more complicated. As I said, this is more like something I would actually give you. I can't remember exactly what I put on last semester's exam, but it was a Lrc circuit. And I'll probably give you an Lrc circuit again, because everything else is kind of as simple as that last bit I just did. It says we have an Lrc circuit. This Lrc circuit consists of a resistor that's 9 times 10 to the second ohms. So 900 ohms. I don't know why I wrote it like that. A capacitor that's 0.25 microfarad. So 0.25 times 10 to the negative 6 farads. An inductor that's 2.5 henries. And it's connected across a power source with a frequency of 2.4 times 10 to the second, or 240 hertz frequency. And I give Vmax as 140 volts. Okay, first off, what's the impedance? Well, the equation for impedance is impedance, which is kind of the equivalent resistance, but not really. It's more complicated than that, but it's how much it acts like a resistor. Impedance is given as the square root of R squared plus XL minus XC squared. Where I showed how we got this using vectors, or also known as a phasor diagram. It was a way of looking at it as if it was vectors. Now to do this, that means I need XL and XC. But I can get both those. XC is 1 over 2 pi FC. And I just did that by memory. Let's make sure I'm right. Yep. So it's 1 over 2 pi times the frequency, 240 hertz, times C. 2.5 times 10 to negative 7th farads. I'm just converting it to a more normal way. And that'll give a value. XL is 2 pi FL. So it's 2 pi times 240 hertz times the inductance, 2.5 henries, which doing that math gives me 3769.91 ohms. And now that I have those, I can put them into my impedance equation. That my impedance is the square root, which I'm going to write the square root at the end again, just for 900 ohms squared plus my X of L, 3769.91 ohms, minus my X of C, 2652.58 ohms, with these squared and the square root of. And in the solutions, I do every single algebra step of doing that, but I mean, it's just calculator. You can get a value. Any questions though?
Nope.
Okay, the next part is what's the max current? Well, I'm going to still use V equals IL. But now with AC circuit, we're not going to use the resistance. We're going to use the impedance. And so V max equals I max Z, which is probably written on. Nope, I didn't bother writing on the top of the page. Mostly because that's just Ohm's law. We've done it so many times. Didn't think it was worth writing again. So I max equals V max over Z, or 140 volts over 1430 ohms. 0.0979 amps. C is the phase angle. Now the phase angle is a way to talk about how much the current lags or leads the voltage. And actually D is the current lagging or leading the voltage. So we're going to be getting there. It's a way of thinking about that if we have an entire wave, we're going to say from here to here is 360 degrees. And so whatever angle we get, that is the ratio that we're off by, lagging or leading. This is commonly used to get, sorry, I'm just going to make it pop up this way. This is commonly used to get average power in a Lrc circuit. You're using this equation here. But for getting the phase angle, and I'm still on the page, is the phase angle is the inverse tangent of XL minus, yep, XL minus XC. I just did that backwards in my mind for a second, which is why I paused, over all. So it's the inverse tangent of 2652.58 ohms. Oh, I did that backwards. That's XC. Know that? I only knows because I color coded it. 3769.91 ohms minus 2652.58 ohms. All of that over 900 ohms. Sorry that I put that upside down backwards for a second. And you'll get an angle. 51.1 degrees. Now, D does that mean lagging or leading? I got a positive answer. Anytime you get a positive answer, that means voltage leads the current. Or you could say current is lagging the voltage, which is more what I asked for. That voltage leads when you're positive, and therefore the current is behind the voltage. Current lags the voltage. If I got a negative answer, it would be the opposite way. And so, yeah, I'll just say current is lagging the voltage. This is probably what's most likely the type of thing to be on the exam. I may also work in Powell. I think I also worked in solving for RMS versus Max just for fun. I mean, I'll do little other bits in there, but this is the general idea. Any questions, though?
I got it.
Cool. So let's go back to typing. Now, that being said, there is a bunch of other things. Wow. So these problems aren't ones I wrote because I like to use the example problems as old exam problems, but since I've only had one semester of exams, I decided not to do it since you're going to see those when I, solve last semester's exam. So they're textbook problems. Textbook problems can be a little dated. And this problem cracks me up just for the sheer a little datedness, but the power cube transformer for a portable CD player has an output of 4.5 volts and 6 milliamps, both RMS. I probably should switch to something else that is slightly more relevant, but here we go. So as an output of 4.5 volts and actually I'm going to write that differently. I'm going to say V output RMS of 4.5 volts and a current out of 600 milliamps. When it's done to a standard 120 volt 60 hertz outlet. So that means we're getting out 4.5 volts, but we're putting in 120 volts. Now, and it says 120 volts the RMS voltage. This is what's going in. Whatever's going in, that's the primary. So really, I should say this is V1. And this is V2. That's what that means. And it says the primary coil, so N1, has 400 turns. How many turns are in the secondary? Well, we know, and it's written up there in the kernel, that V2 over V1 equals N2 over N1. If I multiply both sides by N1, I'll get the number of turns on the secondary is V2 over V1 times N1. Or 4.5 volts over 120 volts times 400 turns. And the answer is only 15 turns. And this works. Like anything that has a big power block, that's half the time what they're doing. They're type transformers like that. The one that comes to my mind the fastest is actually, you know what? Do I have? No, I was about to make it visible the one for my computer, but I feel like there's way too big of a chance of me accidentally unplugging my computer in the process. One that comes to my mind the fastest is like my Xbox. The Xbox has like big one. That's all it is. It's a way to change the voltage to match what it needs for the input. Anything with a power block like that. It's just a transformer.
Okay.
All right.
Also, just a quick question. That's not entirely related, but
Sure.
now that you mentioned the Xbox, like power block thing,
Yeah.
when you unplug it, that little light stays on the block for a little bit. Is that because it has an inductor in it, or is it because it's a little battery that kind of keeps it
It
on?
has all sorts of things in it. But why it would stay on for a little bit before it turns off would be because of, it could be because of inductor, it could be because of capacitors. I don't know exactly what's inside to answer with, but keep in mind when you unplug it, you're very quickly changing the voltage. So an inductor wouldn't do something, keeping the light lit. But also if there's a capacitor, the capacitor will get charged. So when you unplug it, the capacitor will have to discharge. The way that something like that, normally when you unplug, the light turns off pretty quickly. Like it's not like it's, you turn it off and it's like down a few seconds later. I would
Yeah.
say it's more likely it is an inductor than a capacitor. Also, an inductor would be more useful than a capacitor in this case, especially if it is being a transformer. A transformer basically is an inductor, right? Like, if you remember my video of the inductors, it was just loops of wire around a piece of metal. And sorry, I have a transformer.
Yeah.
And this is my inductor. My inductor is a loop of wire around a metal core. So it's the same thing. So it probably is an inductor, but it could be a capacitor. I've never taken one apart enough.
Okay. Yeah.
This is the thing. I'm a
I'm
physicist.
not
I
planning on
don't
taking
work
one
with
apart
practical
either.
things. Sorry, what was that?
I said I'm not planning on taking mine apart either. So.
Yeah. Okay, part B. What is the peak current in the primary coil? Here's the thing. With an transformer, is the power will be the same on both sides. That I1 V1 will be the same as I2 V2. Or, since we had all RMSs here, I1 RMS V1 RMS equals I2 RMS V2 RMS. Because it's power. If I'm doing power, I have to use RMS. Power doesn't really work with max. Now, in theory, this time I could do I1 max V1 max equals I2 max V2 max, just because the conversion is a square root of 2. And so if I do it to both sides and both sides, it would still be equal. It wouldn't be equal to power. And therefore, we're looking for 2 or 1. How many turns was the peak current in the primary coil? Okay, so I1 RMS, I'll just divide by V1 RMS equals I2 RMS V2 RMS. I should put commas here so it's less messy. Over V1 RMS. So 0.6 amps, 4.5 volts, 120 volts, 0.0225 amps. And that would be the RMS current through the primary. Thing is, I didn't ask for that. I asked for the max, but I max equals the square root of 2 times I RMS. And so it's just the square root of 2 times 0.225 amps, or 0.032 amps, or 32 milliamps. Wait, that can't be right. Yes, because it was 600 milliamps. Yeah, sorry. My mind just put this as 0.6 milliamps even instead of 0.6 amps here, and I'm like, what? But yeah, that's right. And that's the idea, that on a transformer, the power is the same on both sides.
Okay.
And let's see, what do we got left? Yeah, I'll do a little more. I'm not going to bother doing all the steps at 4 just because it's very, very time consuming and for not much work. 4 is getting into light, or at least the electromagnetic spectrum, where it talks about radio waves. But radio waves is a type of electromagnetic spectrum. Now, for electromagnetic waves, well, for any wave, we can say the velocity of a wave is wavelength times frequency. But for electromagnetic waves, we can say, sorry, wavelength of wave is, what did I just say? I don't know what I said. The speed of a wave for any wave is wavelength times frequency. But for an electromagnetic wave, the speed of the wave is c. And so the speed of any electromagnetic wave is wavelength times frequency. And here I gave a series of frequencies: 540 kilohertz, 1600 kilohertz, 88 megahertz, and 108 megahertz. And I said, what's the wavelength range for each one? What that is I'm going to take my full frequencies, being 540,000, 1,600,000, 88 times 10 to the 6th, and 108 times 10 to the 6th. And if I want to get the wavelength range, I'll just convert those to wavelengths, where I'll say that c equals lambda f. That means the wavelength is c over f, where c is always 3 times 10 to the 8th meters per second. And so I'll just divide each one by the f. And this is what I'm talking about. I'm not going to bother plugging in each number. Like, it's just you put the number there. And that means for my AM radio band, 540,000 to 1,600,000, my wavelength range will be anything between 555.6 meters to 187.8 meters. Now let's think about that. That means the wave that makes up from here to here is between 200-ish and 550 meters. Radio waves are huge because they do have such a large wavelength. That's why they can pass through materials well. That's why, keep in mind, Bluetooth is what I was trying to say. Bluetooth, Wi-Fi, those types of radio waves. They can pass through material real well because they have these long wavelengths so they can get through the materials. As long as it's not metal, because if you get metal, then you get a Faraday cage and things can get messed up. Pretty sure I talked about Faraday cages a few chapters ago. For FM, my range was 88 megahertz to 108 megahertz. And plugging into the same equation, that'll give me much smaller waves, so between 2 and 3 meters. Well, 2.7 and 3.4. FM doesn't travel long distances as well. Well, it does travel long distance, but it doesn't travel through material as well. But it's still can do it pretty decently. And why not? I'll do the last one today, because the last one's about something completely different. Wow, sorry. And my solution just looks like a mess off the top of my head. So, let's see what I got. Oh, I love this problem. I don't think it'll fit on that page. My last one is about Doppler effect. And I know I said I was going to stop at 25 after normally for these, but it's a fun problem, so I'm doing it anyways. Nope. Yep. Says, a speedo tries to explain police that the red warning light she was approaching on the side of the road looked green to her because of the Doppler shift. So that's the problem, right? You're approaching a stoplight. You run the stoplight when it was red, and you claim, no, it was really, I saw a green light. I saw green because, I was going that fast. Never mind, you don't want to tell the cops you're going that fast. How fast do you need to be traveling for a red light, which red light has a wavelength of 670 nanometers, to look like a green light? Well, green light has a wavelength of 560 nanometers. I have a slight mistake in my solution here that I'll have to fix. but I'll come back to that. See, what we're saying is the real wavelength was red. So I would say this is what came from the source. But we saw green. So I'm going to say that's what the observer saw. And we're saying for it to shift this way, you'd be approaching the light. So I'll say using the approaching equation that the F observed is the F of S square root, and I always got to check this so I don't get it backwards, C plus V over C minus V. Now, this is not an easy thing algebraically to solve because I need to solve for V and there's two of them in the square root. So I'm going to walk you through the process for solving it. I would divide both sides by F of S. I would then square both sides. And I'm just going to factor out my squared for no apparent reason. No. I don't want to deal with this fraction here, so I'm going to multiply both sides by C minus V. I don't know why I bother with parentheses on that side. I'm then going to factor this right side out. And I'm going to get all my V's on the same side. So I'm going to subtract this C from both sides, and I'm going to add this V to both sides, giving me C F naught over F of S squared plus C equals, I'm adding this over, V F naught over F of S squared plus V. Make sure I didn't make a math error here yet. Nope, I subtracted that C. I did. Because I subtracted the C, so it became negative. I decided to factor out both sides, which would be C F naught over Fs squared minus 1 equals V F naught over F of S squared plus 1. I can then divide and get V equals C F naught over Fs squared minus 1 over F naught over Fs squared plus 1. You could solve it here. With a tiny bit of work. But what did I do? Oh, I found it in terms of C. I didn't plug in C and I found it as a ratio of C. So yeah, I can solve it here, but here's the thing. These are frequencies. I gave wavelengths. But we know, let's do a quick aside, that C equals lambda F. And therefore, F naught equals C over lambda naught. And Fs equals C over lambda S. Now, both of these have an F naught over Fs. So if I just say, let me just go up a little bit, F naught over Fs, which I know will be squared, will be C over lambda naught over C over lambda S. My C's cancel. It gives me 1 over lambda naught over 1 over lambda S, which is the same as lambda S over lambda naught. And so this equation in red becomes V equals C lambda S over lambda naught squared plus 1 over lambda S over lambda naught plus 1. This is a minus 1 squared. Where the C is times the whole thing. So I want to quickly look at my solutions, make sure I didn't do a math error somewhere. I didn't. That is impressive. And now I can plug in. I'm going to take up a little more space and say V equals C, 3 times 10 to the 8th meters per second. I'm not going to bother converting it to nanometers because they're all ratios. 670 nanometers over 560. You know, let's just do that real fast. 670 nanometers over 560 nanometers. Doing that math, that's 1.196. So V equals 3 times 10 to the 8th meters per second times 1.196 squared minus 1 over 1.196 squared plus 1. And that will eventually give you a speed of 1.19 times 10 to the 8. Oops, that's a lie. 5.32 times 10 to the 7th meters per second. Now, for the record, just so you know, I converted this. This is the other number I was writing. That equal to 1.19 times 10 to the 8th miles per hour, which is known as Mach 156,337, as in 156,337 times the speed of light. So the amount of speeding ticket you would get for doing this is pretty impressive. Never mind, you'd be traveling at relativistic speeds and many times faster than anything we've ever created something moving at. So, you know, you probably get a really bad speeding ticket.
Probably
But
lose your license.
Yeah, you'd actually probably wouldn't survive the accelerations or decelerations to do that on this planet. But yeah, that's how fast you'd have to be going. You'd have to be traveling at 5.32 times 10 to the 7th meters per second to see a red light and think it was green. There you go. So end today with that, unless there's any questions. Next chapter, we're just doing optics. We are done with electricity and magnetism, other than the homework and the lab that was just released.
Any exam?
That's what I like to hear.
Yeah. Oh, sorry. Yes, and then the exam. The exam will have some. Time to do optics. Optics, honestly, is a lot simpler. Not many equations. They're all pretty straightforward. But yeah, that's where we'll leave off. Other than that, have a good weekend. I'll see you guys Monday.
Yeah. Have a good day. Have a good weekend.
Have a good weekend.